Hey everybody, today the Fearless Teacher presents Relations, Functions, and Equations, a review. Let's talk first about what a relation is. A relation is any set of ordered pairs. For instance, if I have the set of ordered pairs 1, 2, 3, 1, 2, 4, and 1, 3. The domain of this relation are all of the x coordinates, which would be 1, 2, and 3. Notice that I have two ones, but I only mention it one time. So it would not be 1, 1, 2, 3, and I'm going to put them in order too. Then the range of this function is going to be 1, 2, 3, 4. Once again, I'm putting them in order instead of out of order. So the domain and the range. Okay, now let's talk specifically about a function. A function is a special case of a relation. And the definition is, a function is a relation where each element in the domain corresponds to exactly one element in the range. You should remember this from Algebra 1 and Algebra 2. All functions are relations, but not all relations are functions. For example, go back to our example up here in the pink. We have 2 points that have the same x coordinate but different y coordinates. So that does not, that means that the domain corresponds to exactly one element in the range. It doesn't. One corresponds to 2 and one corresponds to 3. So that is not a function. It's just a relation. Everything's a relation, but only special cases of relations are functions. Okay, let's take a look at our coordinate system. We call the ordered pairs either x, y. We can call them the domain range. We can call them the independent variable and the dependent variable. It all means the same thing. The independent variable, x domain, is on the x-axis. The y range dependent variable is on the y-axis. The question now is, when does an equation represent a function? When does an equation represent a function? Well, if you remember the vertical line test, if we can draw the graph of the equation and we can spot any place with the vertical line where the vertical line touches 2 points, or more than, and could be more than 2, more than 1 point on the graph, then it is not a function. So let's take a look at 3. We're going to do y equals x squared plus y squared equals 4, and y equals 3x. For the first one, that's a parabola. And there's nowhere on that and the second one is a circle, and the third one is a line. Okay, going back to the first one. When I draw vertical lines, there's no place on that graph where I hit the blue graph, not the x-axis, the blue graph more than one place. So, yes, that is a function. With the circle, well, there's a lot of points that I can find where I'm hitting the graph in 2 places, and here's 2 examples. If I go way out to the left, it's no places. If I go right tangent to the circle, it's 1 place. But all I have to do is find 1 place on that graph where I can draw a vertical line and hit more than 1 point on the graph, and it is not a function. And the third one, y equals 3x, well, that's a linear function. And there's no place that I can do my vertical line and do anything other than hit that line in one spot. Remember, the only line that is not a function is a vertical line. Okay, so that is a function. So let's move on. Let's talk about function notation. Normally we have x, y. That's what we're used to looking at. But in function notation, we substitute, instead of y, we substitute f of x. F of x means a function of x. So this coordinate would be x, and then the y coordinate would be the function of x. So let's do a couple examples. We're going to do f of x equals x squared minus 1, and I want to find f of 2. That means everywhere I see an x, I'm going to substitute a 2. So that's going to be 2 squared minus 1 which is 4 minus 1, which is 3. So I would say the ordered pair would be 2, 3. The 2 corresponds to the domain, or the x, and the f of x corresponds to the range, which is 3. If I do f of x equals x squared minus 1, and this time I want to substitute f of minus 2, then everywhere I see an x, I'm going to substitute minus 2. So I'll have minus 2 squared, and remember that's minus 2 in parentheses squared, minus 1, which is 4 minus 1, which is 3 again. So I would say f of minus 2 equals 3, and minus 2, 3 is my coordinates of my solution set. The minus 2 corresponds to the x, and the 3 corresponds to the f of x. Okay, let's evaluate f of x equals x squared plus 3x at f of x plus 2 and at f of negative x. So what I'm going to do is I'm going to take my the evaluate f of x equals x squared plus 3, and in x squared plus 3, everywhere I see an x, I'm going to substitute an x plus 2. So this will be f of x plus 2 equals x plus 2 squared plus 3 times x plus 2. And if I just expand this, x squared plus 4x plus 4 plus 3x plus 6, and I gather my like terms, I have x squared, and then I have a 4x and a 3x, gives me 7x, and I have a 4 and a 6, gives me 10. So I have f of x plus 2 equals x squared plus 7x plus 10. If I want to evaluate f of negative x for this function, everywhere I see an x in the x squared plus 3, I'm going to substitute a negative x. So I'll have negative x squared plus 3 times negative x. And once again, that negative x squared is in parentheses, so that's going to be x squared minus 3x. So f of minus x is x squared plus 3x. Let's see if we can identify the domain and range of a function from a graph. So we're going to do some graphs here. The first one is going to look like this. It's kind of a funny looking graph, and we're just going to say f of x equals that green graph. The second one is going to look like this. And if it doesn't hit exactly, we're going to pretend like everything hits right on a whole number or an even or an integer. And the third one is this kind of curvy thing that looks a little strange. So anyhow, I need to identify my domain and my range. Domain is where the x values start and stop. Okay, so the domain of this function, if I do vertical lines, I can see that my domain actually goes from negative 3 to positive 2. At negative 3, I have an open dot, so I'm going to be using a parenthesis there because it does not include that. And at 2, I have a closed dot, so I'm going to be using a bracket, which means it does include that. Now the range is how far up and down it goes, so if I do some lines here, I can see that my lowest number in my range is 1, and my upper number is 3, even though my graph isn't drawn very well, and 3 is included. Notice we're not talking about the endpoints of the graph. We're talking about the lowest point of the graph and the highest point of the graph. There is the highest point of the graph, and that is on the graph, so we would have our bracket there. Okay, so the next one. The domain is going to go from the numbers minus 2 to 4. Minus 2 is included because it's a closed dot, and 4 is not included because it's an open dot. Now if I want to look at the range, I'm going to look at the up and down movement, and I notice that my smallest value is negative 1, and my biggest value is 2. Negative 1 is not included, but 2 is included. In my last one, my domain goes from negative 2 to positive 4. The positive 4 is not included. The negative 2 is included. As far as the range goes, it goes from 1 to 3, 1 is included, and 3 is included. It's not that last point that has the open dot. That's not the tallest point on the graph. 3 is the tallest point. All right, intercepts. Intercepts are where the graph crosses or touches an x-axis or a y-axis. Any axis. So if I have this graph, and I got this little squiggly concoction here, I can see that that graph touches the x-axis in 3 places and touches the y-axis in 1 place, which brings us to this. A function may have multiple x-intercepts, but at most 1 y-intercept. Otherwise, it would not be a function. Okay, go do your checkpoints, folks. See you in class.